Seth, thank you for organizing. Thank you for the opportunity to present, and thank you all for joining today. I'm excited to talk to you about building NLP models faster, and specifically with distributed training. As Seth mentioned, my name is Dave Triano. Awesome job on the last name pronunciation, by the way. And I am a solutions engineer with Determinate AI. At Determined, we build an open source platform specifically focused on deep learning model training. Distributed training is one capability in that platform, and I'll touch on some of the others, but the focus for today is definitely going to be on distributed training. And if you don't know what distributed training is, no worries. We'll talk through that. Okay, so for kind of the three phases of the talk today. The first one here, I'm going to breeze through this because I'm pretty sure that this group, I don't have to talk about the promise of deep learning for NLP. So I'll kind of breeze through that part. I'll show a demo specifically around BERT fine tuning with Determined, and we'll kind of get into distributed training as part of that, so you can see it in action. And then finally, I'll present some results that we came up with for a couple of different kinds of models. One is for a BERT model, and then one of BERT's successors or children, if you will, Albert. And we're really focusing on kind of like massive speed up here by 1 to 2 orders of magnitude, 10 to 50x speed up in terms of wall clock training time. Deep learning for NLP, I think both talks here today are going to talk about, they're going to have some mention of deep learning. If you look at any kind of NLP conference, they're sort of dominated by deep learning. And pick your favorite NLP task. The proof is in the pudding. I think especially as you look at the past couple of years, here we're looking at kind of state-of-the-art named entity recognition performance on one benchmark. And over the last couple of years, like every model here that you're looking at is using a neural language model under the hood. So I think the same goes for question answering, predicting next tokens or next sentences, things like that. So I think we're all kind of seeing NLP enjoy the benefits of deep learning, just as computer vision did kind of previously. The cost or the challenge, I think, of this is that sort of doing it end to end, like just starting from text, coming up with a neural language model, and then solving your NLP task is sort of unrealistic for most organizations. In particular, there's a ton, very high research cost for that. And the models themselves are really only kind of getting bigger and bigger because they're performing better and better as they get bigger and bigger. So you'll see headlines about models with, hundreds of millions or billions even of trained model weights, and headlines about kind of the dollar cost if you were to try to replicate these. The carbon footprint cost, et cetera. So for most folks, unless you're at, say, Google or a large academic institution, the saving grace for us is kind of multi-stage transfer learning, right? So you take a pre-trained model, for example, BERT or GPT. That language model was trained on maybe Wikipedia or Brown corpus or both or some other corpus. You kind of use that as your starting point, and then you adapt that, and that adaptation or fine tuning is typically way less expensive. And in the pictures here, the example for BERT, training a BERT model for Q&A, you're basically changing the inputs, changing the outputs a little bit. Maybe for some problems, you might have some downstream layers that you're training, but in general, it's way less expensive to do this kind of thing. So we can all kind of, solve problems with NLP in, tens or maybe hundreds of dollars rather than, the scary kind of like tens of thousands of dollars or even some of like the $1 million headlines that we see. How this actually works in practice for a practitioner, when you're prototyping an idea, it generally kind of starts with maybe a paper, maybe you find some code on GitHub. Maybe you start from a library like Hugging Face, like Spacey, like John Snow Labs, and that's kind of your starting point. And then you procure some infrastructure. Maybe you can just sort of do your prototyping on a laptop. But if you need a GPU, you can, kind of spin up a P2 instance on AWS or something like that. And then you go about your job and develop your model. So you grab your own documents or text, let's say. You dabble in PyTorch or TensorFlow, maybe play with featureization, play with the model itself. Jupyter Labs often comes in, or Jupyter Notebooks often comes into play as you sort of iterate. And then you decide, like, do I have something compelling here that maybe can go to production? And hopefully the answer there is yes. And then when you want to go to production, things kind of, they get a little bit scarier for data scientists and practitioners, because all these problems or kind of hurdles come into play. And when I talk about productionizing an idea like productionizing an idea like that, I don't really mean like just taking that trained model and serving it in a live use case. Like, I'm really talking about treating your solution to that problem like almost as a software engineer treats their software, right? It's a never ending, you're always improving it. You're always kind of adopting the latest and greatest technologies or new libraries that are out there. If you're a software engineer, in the NLP case, maybe you're adopting the latest and greatest models, right? Like, after BERT came out, there was no Albert. Albert came out and it's like, oh, this model's a lot smaller, and it actually, seems to perform a lot better. Let's try that out. So all these problems they're not really like, or all these hurdles again are not really like NLP or data science in nature. Aside from maybe tuning hyperparameters, training models faster, right, and there we're going to really talk, kind of dive in on distributed training. These are mostly software infrastructure concerns, or kind of what I would call like software engineering, like harness, things that you have to do in harness, right, for like tracking models, tracking metadata, tracking metrics, making your jobs that, take a day to run, making those fault tolerant. Like, all these are kind of things that are sort of outside what the NLP practitioner cares about, which can, make the NLP practitioner sweat a little bit because they have to worry about these things. I'm going to move quickly through this slide because that's pretty graphic. But, so this is all kind of set up for our platform, Determinate AI. Our platform basically gives the practitioner a platform on which they can still, continue to work with the tools that they like to use, whether that's working in TensorFlow or PyTorch, and kind of associated tooling that is almost baseline, like tensor boards or notebooks, sort of giving them an experience where they continue to use those tools for model development and training, but they don't have to worry about software infrastructure concerns. They don't have to worry about things like fault tolerance and experiment tracking, things like that. So this is sort of where we fit in the machine learning ecosystem, right? Like, sort of post of data management and preparation and pre-model serving. A quick look at the capabilities in particular. I'll touch on some of these, especially as we demo. You can see them live. For today, of course, we're talking distributed training, right? We're talking about taking a model that takes, a day and a half to train and getting that runtime down to, say, an hour or a half hour even. Okay, so with that, I'm going to jump into a live demo now. Let's fix my window. Okay, so for this particular demo, so we're going to look at a fine-tuning use case. So this is BERT for question answering. So this is a fine-tuning application where we're basically trying to solve this problem where we're building a model that can take a paragraph or a context and a question whose answer is likely in that context and extract the answer from it. So sort of an important application for things like virtual assistants, Our demo here, so this is going to be on one benchmark in this task, squad 1.1. So without further ado, so I'm going to deliver the demo from this notebook here. The Determine platform itself, so I'll kind of jump back and forth. I'll jump back and forth here to the Determine web UI. Determine itself, you can interface with via CLI, via Python SDK. The web UI is also sort of kind of an awesome one-stop shop where you can kind of see what's up on your cluster, right? How many resources do I have available to me to train? What kinds of experiments have been running, are currently running? So for example, here I can see I have, one GPU in use. I have 8 available to me in total. That GPU happens to be attached to this notebook. And with that, I'm going to kick off a couple of experiments here. So the first one is going to be that just train a single model experiment. So I'm going to kick that off. As I kick that off, that's going to start using one GPU here. So we can see one GPU in use. And this BERT squad constant hyperparameter experiment is now kicked off. The other experiment I'm going to kick off, I'm going to take a quick little detour into hyperparameter tuning as well, even though that's not the focus here. But just to kind of give you a sense for the other things that you can do with the platform, I will kick that off. Now, because we're tuning hyperparameters, we are going to train many models, and I'll show you some of the hyperparameters that we're going to tune. But because we're tuning hyperparameters and training many models, those models are going to be trained. We're going to parallelize that training across many GPUs. So you can see all 8 GPUs in use now. Under the hood, because this cluster is in the cloud, it's actually running in GCP. We will spin up instances in response to this, and you'll kind of see the fleet of GPUs grow as we go in order to run these experiments. Now, just to give a quick look for what it means to submit an experiment. So for that first one that I submitted, there's basically a spec for that experiment. Make this a little bit larger. And about half of that spec is what we call hyperparameters. And the hyperparameters are, they kind of vary in terms of sort of the flavor of hyperparameters. So things like document stride and max query length are, specific to featurization, like basically how you're taking text and tokenizing it and actually getting it into input features into your network. The majority of the rest are all around the learning process itself. So, things like learning rate, the epsilon for the atom optimizer that's being used. The only sort of determined specific required hyperparameters is this global batch size here. That is basically the number of records, basically the size of each mini batch as we're training. And global batch size will come into play in a little bit as we talk about distributed training. So we'll just kind of keep that in mind. And so we submitted this experiment. Going back quickly to hyperparameter tuning, just to sort of show you, I guess the point of hyperparameter tuning and then how you do it on the platform. The point of it is very simply to find better models, right? Find more effective models. You can sort of very easily try a different learning rate and get a much less performant model in terms of validation accuracy. So hyperparameter tuning is all about kind of defining a search space for hyperparameters like this. And then applying a search algorithm to those to find a better model. So the first thing you'll notice here in terms of looking at the hyperparameter tuning experiment is that we're providing ranges for some of these. So a couple of the featurization hyperparameters are now allowed to vary. And then similarly, we have for the learning process itself, some hyperparameters like learning rate can vary logarithmically, and we give ranges. You can do categorical variables, all this fun stuff. So we now, you define space, and then you define a way to search that space. And in this case, we're saying, we'll look at over 100 different points in this space, and we will apply one of our adaptive searchers, which is based on an early stopping technique, and kind of let it chug. So I'm going to show you what this looks like when it ends. As you can see here, experiment 60 to 64. I ran a little bit earlier today. But at least that hyperparameter tuning one that runs, tons and tons of trials, that took a little bit over an hour to run. So I'm just going to show you kind of the final result here. But basically what you get is, as part of this run, we're running many trials with different hyperparameters. And you can sort of see this converges actually very quickly. So this graph up here is basically the validation accuracy F1 in this case, the best one that we have observed across all of these different trials. You can see like pretty quickly we get up to 69 and then exceed into 70, compared to the first one that we ran. So this is just another instance of that finished earlier. Achieves maybe high 60s, let's say. If you're familiar with BERT on Squad, these are not groundbreaking numbers. The reason for that is that this is actually running on a subset of Squad to make the runtime tight enough to run in the context of a demo. So I'll show you in a little bit full metrics when we run on a full data set. And we'll get up into the more expected kind of high 80s range. Cool. So we've looked at training a model, tuning hyperparameters. Let's get into distributed training. So this is sort of the meat of the talk now. I'll talk about what this is and how you actually do it. So how you do it first. One thing that you can do with distributed training and with the platform in particular is let's take one of our winning trials of this hyperparameter search that achieved pretty good validation score of 70. And we can just continue this trial. So maybe we'll train it on additional data or just train it for longer, right? So let's say I want to actually train this for 4 times the number of epochs, right? We trained for 2 epochs before, let's actually train it for 8. And then the only things that you need to do to train distributed now is just specify your degree of parallelism. So we're going to run one trial here, and I'm going to say, let's just give this 4 GPUs instead. Okay, now and then the only other thing that we need to do is also increase our global batch size. The reason for this is that we basically want to keep, at least for this example, we're going to keep the batch size per GPU the same. So by multiplying this by 4 also, we're now keeping the batch size on each GPU to 2. And we can kick this off and activate it. I'm actually going to pause one of these running experiments just so that we can free up some GPUs for the experiment that I kicked off. And we'll see that kick off very briefly here as that hyperparameter tuning experiment pauses, and we'll use up 4 GPUs and we'll be off to the races. To show you, so while that's happening, just to show you how this actually looks when it's complete, experiment 64 down here is exactly what I just did. So if I view this configuration, I can see I specified slots per trial of 4. My global batch size was also 8 over here. So same exact experiment. And you can basically see just in comparing the runtime that it's pretty much the same as the constant hyperparameter experiment. So each of these is taking about 10 minutes. So the kind of the key here that I want to get across is that, we're training for 4x the amount of data, right? We're training for 4x the number of epochs. We threw 4x the number of GPUs at it, and we're scaling more or less perfectly. Actually, a little bit better. It's a little bit noisy because there are startup costs and whatnot. But this is basically the idea of distributed training in a nutshell, right? Take blow up these times to something more realistic, like hours, like a day and a half. Throw even more GPUs, right? Throw 64 GPUs at it, and get training run times down from a day and a half down to 40 minutes or something like that. So this is the idea of distributed training. Let me pause and see if there are any questions so far. Okay. So great question here. What do you mean by distributed? Is it model or data distributed? I assume you mean parallel rather than distributed. Okay, so that's a great question. And I'm going to jump right into that in slides now. So what do we mean by distributed training? And in this case, the study is going to be around the same BERT model, although training on the full squad data set. We're using the model that comes from Hugging Face. And our baseline is basically training on a single GPU and then training on multiple GPUs, and then kind of optimizing for scale efficiency as we go there. So I'll get to the definition of what distributed training is in a second. It is data parallel, and I'll show you some pictures of how it's actually working. Our baseline here, so you can see we hit about 6.7 hours here to train on a single GPU, one of the kind of more cost-effective GPUs, a K80 on GCP, fine-tuning for 2 epochs. We achieved pretty good validation accuracy, around 88%. Okay, so what happens when we scale up in the same way that we just did for the demo? So this is what we call weak scaling. You increase your number of GPUs and then accordingly multiply out your batch size. So your per slot batch size is basically the same. And you can see that we get pretty good results here. I mean, in absolute terms, we get training down to an hour. Scaling efficiency is okay. Perfect scaling efficiency would be, at least for 8 GPUs, would be more, going from like 400 minutes down to 50. We hit 60. So not bad. You can, though, see kind of a clear, downward trend in scaling efficiency as we go. So something's going on here. And to kind of dive into that, I'm going to show you now what this looks like in a picture for distributed training. And to do that, we'll start just with single GPU training. So you have one GPU, you have your model, and we sort of just very, in very boring fashion, like send a batch through, making forward and backward passes until we're at the end, right? Until we train for however many epochs. So each subscript here is basically specifying a batch. With distributed training in Determined, it is data parallel. So the idea here is that you're taking your input data set, you're going to shard that. So here we have 4 GPUs. We'll shard our data set into 4. Each GPU is then going to independently train a model. So each GPU has its own copy. And then the process goes like this. So each one sends a batch through, does a forward and backward pass, and then there's this communication step. The communication step is basically reducing gradients so that at the end of it, every model will have the same weights, right? And then you just continue this process of forward, backward pass, communicate. Under the hood, the backward pass and communication is happening kind of simultaneously with how we optimize things. But this is the general idea. And with the timeline here, you can kind of see this is sort of meant to be by scale. You can sort of see that as you throw 4 GPUs at a problem like this, assuming your batch size is the same, in general, you should be able to train for about 4x the amount of data in the same amount of time. Might be a little bit worse, right? Because this communication is not for free. So we'll look at ways to basically optimize that, right? Communicate less often, communicate more efficiently. The sort of easiest way to do that is to just use bigger batch sizes. So I'm kind of showing that with bigger font size here, right? Like let's say we double our batch size, then in order to train for the same amount of records overall, we would have to communicate half as often, right? This can be problematic, right? So very quickly you can run out of GPU memory. So one way around this, and one kind of knob at your disposal in Determined, is what we call local gradient aggregation. So the idea is that rather than increasing your batch size, you're going to increase your effective batch size, but under the hood, you're just going to run 2. Let's say with frequency 2, you'll run 1 batch through forward and backwards pass, and then the next one before communicating. So you can use frequency 2, 4, 8. In practice, something, single digits or low double digits tends to work pretty well. But in this case, similar to doubling your batch size, by increasing your frequency to 2, you communicate half as often compared to that baseline example, but also don't sort of blow up your GPU memory. Okay, so let's look at some results with local gradient aggregation to see if it kind of helps. And you can see that it does help runtime pretty significantly, right? So by increasing aggregation frequency to 2 and then 10, we shave off pretty significant time from our training, which is good. Even just going to aggregation frequency 2, we shave 15 minutes or so off of our training time. Which is that's good, that's significant, right? This is basically saying that communication was our bottleneck and a big opportunity to improve. But you can kind of see validation accuracy now ticking down. So we're playing a little bit of whack-a-mole here, solving the time performance problem, but validation accuracy is hurting. So why is that happening? And in general, it's because large batch training is, it's hard. There's model convergence in particular is pretty tricky. There's sort of heuristics out there for either scaling or warming up your learning rate to make this happen. Or sorry, to make training more effective in this scenario. That didn't actually help in this case, but what we've found in this example and in others is trying a different optimizer. So in this case, there's a family of adaptive learning rate optimizers out there, Atom being one of them. There's a very recent optimizer that came out called R-Atom, R for rectified, I believe, that is basically designed to be more robust, especially for large batch training. So it's sort of dynamic in how it does the adaptive learning rate. And as a result, you can kind of see the results here as we go from 2 to 10 to 100. Training time is good, and we're addressing that, but our validation accuracy also kind of stays nice and high. The 100 here is more kind of to show robustness, even sort of in extreme circumstances. We only shaved a couple, 2 minutes off of the total runtime. So not like a huge bottleneck, not a huge opportunity for improvement. But just to show that we actually, we still stay above 80, which I think is pretty good. Okay, so we did 8 GPUs. Next couple slides are about, let's keep going, right? So 8 GPUs on a machine is kind of typical. In some cases, at least for GPU or for GCP, it's actually the max that you can get. But what if you want to do more, right? Like there shouldn't sort of be this like, I hit a single machine. What do I do when I want to go multiple machines? And the single and multiple machine transition is one that's often problematic to do. With Determined, you get it for free. So actually in the demo itself, when we ran on 4 GPUs, that was actually running across 2 machines under the hood, 2 machines in GCP that each had 2 GPUs attached. And so when we ran this, and ran it with aggregation frequency 2, we got our training time down even more and kept our validation accuracy in the 87% range, which is pretty good. So let's keep going. So this is sort of latest and greatest result. So now different model. So this is using Albert, and let's just keep multiplying by 2. So in this example, we're looking at training Albert. The baseline here was actually much longer. It was like a day and a half. And in going from 1 to 8 to then 64 GPUs, we can actually see like pretty good scaling. I think this is in the like 70 something percent scaling factor, which is really good for 64 GPUs, and gets training time down to 40 something minutes. So huge result. This is coming out in a blog post very soon. So I would say keep an eye out, give us a follow on Twitter. That one, again, the Albert one will be coming out in, I think, within the next like week or 2. And then, yeah, as I mentioned, we are open source. We open sourced earlier this year. I always recommend folks just start on GitHub, go from there, and then you can kind of look at documentation, join us in our community Slack. Feel free to email me, reach out and chat. And with that, that is the end of the talk. So I'm going to jump to questions here.
You have one question in the chat. Do you share the code? And you just answered that.
Okay. Yep.
One in the chat and two in the Q&A. If anyone would, we have about 5 minutes for questions. If anyone would like to be voice enabled to ask your question, use the Zoom raise hand feature, and time permitting, I'll enable you.
Yeah. So for the other questions, have you considered supporting Onyx for model export? I'm actually not sure about Onyx. I'm going to have to dig into that one and follow up with you. In general, so for model export and determined, I actually didn't show this in the demo just for the sake of time, but we do have a model registry that you can basically write code like this. So I can say, you know, let me take experiment, I think it was 61. Let me create a model that can then be versioned and annotated and organized, register a new version. And then of course, from that registry, I can also pull checkpoints out like this with, you know, with code like this, write a couple lines of code to then get your model to then run predictions like this. That format of the model will be sort of framework dependent, whether, you know, depending on it, whether it's TensorFlow, Keras, PyTorch, the format there will be kind of framework dependent, but I'll have to follow up with you on Onyx. Another question here, do you apply any kind of partitioning or bucketing on the data to reduce shuffles? Okay, yeah, so another great question. I would say we've, with customers, we've run into this thing in the past, and there are a couple things that you can do. One is that you can leverage an upstream framework that solves problems like this. So so Uber, for example, has Petastorm, which I think helps with this kind of problem, and in particular helps a ton with distributed training. So that's an option. The other thing that I would mention that we do that helps with this is going back to the product kind of, you know, high level architecture diagram. This deep learning data cache that we have is basically helps with solving this problem as well. So it was specifically designed for TensorFlow data sets, which have trouble with shuffling and random seeks, which makes it kind of tricky, you know, harming performance and correctness, let's say, for deep learning training. So this data cache itself is basically a layer that can help with this problem and enable those capabilities, especially for TF data sets. Cool. Any other questions? I know we're probably about the halfway point. So Seth, keep me honest here, and if we need to transition.
Yeah, you have a question. You have time for another question, which is from David Cleary in the chat. What other tools can be used in combo? Do you recommend using in combination with distributed training? So other tools.
Oh yeah, that's a great question. So so one thing that you can do, for example, in combo is even just looking at this picture, like you can combine distributed training with hyperparameter search as one example, right? So let's say you have, you know, you have hyperparameter search where you're training, you know, many models likely. You have distributed training that can train a single one of those models across multiple GPUs. You can very easily combine these two. So just as we saw with a hyperparameter tuning experiment config where you define ranges and a searcher to do the optimization, you can also just say, okay, let me do 2 or 4 slots per trial for each of those trials. So you can do that sort of thing. And then all these other tools, like I didn't show integrated TensorBoard, but everything that we offer, those kind of baseline capabilities like TensorBoard, you get along with distributed training.
I want to tackle one more from the Q&A. Do you provide explainability or interpretability options against sensitive data training for compliance, especially when the training is distributed?
Yeah, that's a great question. So at Determinate, we don't specifically have explainability or interpretability features, at least yet. You know, my understanding, and one of our co-founders, Amit Talwalkar, he's a professor at CMU, explainability is one of in deep learning is one of his kind of big research areas. And as I understand, especially in listening to him speak, interpretability for DL is a young field, and there's a lot of work to do there. So it's pretty young. We don't have anything in particular there. I think on the security side, where's this question, Seth? Just so I can take a look.
It's in the Q&A.
Okay, sorry. Sensitive data training for compliance, especially when training data is distributed. Yeah, so I would say on the, on more of like the information security side, I know we have deployments where, for example, you could have multiple users using the platform, each kind of having their own credentials that they can use at runtime. So in that way, you can basically get separation by user. So we've seen that sort of thing, which I think is related to this. It's not really an explainability issue, more of kind of access control.
Okay.
Cool.
Well, we're going to stop there. Thanks very much, Dave. I appreciated the talk. I see you shared your slides, and so I will post those to the meetup pages in a comment where I can, along with the URL for the video when that's available. I'm going to enable Antonio Linari to join us now, and Dave, you can revert back to an attendee and stick with us, I hope. And once again, thank you very much for presenting today. So we're going to transition directly to our next speaker, who is Antonio Linari from Expert System. And he is going to be talking about hybrid NLP on edge computer, same protocol. Antonio, please welcome. Thank you, and please introduce yourself and go right to it.
Thank you. I hope you can hear me.
Yes, it's good.
Cool. So yes, this is Antonio Linari, the Chief Technology Officer of Expert System Enterprise in North America. And well, I've been in the technology for more or less 20 years and 15 years in the natural language processing. I've been a coder, I think I was 11 more or less when I started coding. Coded on a paper. Okay, but then I started coding on a real computer. And today I will introduce you something related to hybrid AI, and particularly natural language processing running on Jetson Nano, NVIDIA Jetson Nano. I will start sharing my screen. Okay, so what we are a semantic company, so we have a proprietary technology that is able to ingest the text and perform a full word sense disambiguation using a semantic network. I will be more detailed later. Okay, and the issue that we had was to try to find a way to compare our technology to the other technology, like BERT, for example, like other algorithms, okay? And we wanted to find a way to measure the quality of our technology. And so we came up with some ideas. There are no really useful annotated corpora for doing this job because we have our semantic network. So for example, Semeval is based on WordNet, but we are not WordNet, okay? And so we had a problem with an existing annotated corpus. And it doesn't make any sense to annotate one just because it would be has, so it's not objective, it would be very subjective. And it kinds of takes time to, in any case, to prepare it. So a possible solution that we found was to measure the quality in an indirect way. So basically, using some traditional deep learning or machine learning NLP problem and put ahead of it our technology. In this case, today we're talking about sentiment analysis, and we will use as a reference corpus the IMDb database that, as we know, is a movie reviews. And just because we wanted to see our technology working on small devices, so we don't really need to scale on big GPUs and big infrastructure, even if we can, okay, it depends on the volume that you want to process. But The demo today is running completely on a Jetson Nano. And the only things that is not running on the Jetson Nano is, of course, the browser, but just because there was no time to set up all the stuff directly on the Jetson Nano. So it's going to be a live demo, so we will see live what is happening. First of all, let's get some information from our little device. As you can see, there's a NVIDIA Tegra, there's the GPU. At the moment, there's nothing allocated. And so we are using Torch, and in particular, we are using the GPU. We will import some libraries that we need to, in order to run our demo. And in the meanwhile, we can explain how this ambiguation works. So basically, we have a text coming from whatever source we want. It could be a web page, it could be an email, everything that can be transformed into text. Then the text is passed through an NLP pipeline. It's very traditional pipeline, with the difference that we have also the word sense disambiguation. So basically, we have sentence splitting, the tokenizer, part of speech, there's the lemmatization, the dependency parser, and at the end, there's the word sense disambiguation. What we mean, it means that we are able to assign to every single word in the document or in the text a meaning. Okay, and the meaning is based on a semantic network that counts more than 300,000 nodes or concepts, okay, and millions of relations. Here is an example of what we mean for a semantic network. So basically, it's a graph. We call it a knowledge base. Okay, it's a knowledge base because it provides a tool to learn the reality. I like to separate a knowledge base from a knowledge graph because the knowledge base is kind of a primitive phase. Okay, it's something that gives you really the basic concept that allows you to get the reality. And then there's the events and facts that rely on a knowledge graph. Okay, but basically a knowledge base is a graph with concept, and those concepts are related to each other through relations. And for example, in this case, we have, for example, a fish. A fish is an animal, and a mammal is an animal. And for example, a fish has a relation that lives in water and so forth. Another classical example that we have is the word jaguar. Jaguar can be ambiguous because can mean the animal or can be in the car. And so this ambiguation and the semantic network just helps to remove this ambiguity. So let's do some setup. So basically, what is running on the Jetson Nano is an instance of our, we call it disambiguator. Okay, it's a technology, a proprietary technology based on the semantic network that we just talked about. The name is Sensigrapho. Okay, and we see. So what we are able to do is that given this simple sentence at the moment, it was just to check that everything works correctly. Okay, we are able to transform a sentence keyword based into a sentence concept based. So you can see that, for example, the is and example are now two numbers, and those numbers represents the concept to be and the example in our semantic network. And you see here all the single tokens with the part of speech, with the role in the dependency parser, and the ID in the semantic network, and also the definition, the gloss. Okay. Here you see exactly what is the process. We have a sentence. The sentence goes through the disambiguator, and the output is something that gives also some concept. So it gives those numbers that, as we said, represent concepts. So how we want to measure the quality of our technology? Well, for simplicity, we started by using the, there's an error, I'm sorry, this is not unified, it's universal language model fine-tuning, okay? And we trained from scratch the ULM-fit model using our technology. Just for giving you a short introduction to ULM-fit, ULM-fit is oh my God. Okay, here you can read the paper. It's something that came out in 2018 from Jeremy Howard and Sebastian Ruder, and is basically one of the first attempts to use transfer learning to train a big corpus, like for example Wikipedia, and then specialize this big corpus through the fine-tuning, the same that does BERT in a probably better way now today. So. But at the time, maybe today for some specific applications is still very accurate. So, and these ULM-fit algorithms introduce two particularly interesting things that I'm going to show you here. Here it is one is the discriminative fine-tuning. It means that for every layer of our neural network, okay, we use a different learning rate, and the learning rate varies, using these slanted triangular learning rates. So basically, during the iterations in the training process, okay, the learning rate first increases and then decreases. So going back here, you can see that here, the same structure of the neural network, so a 3 layers LSTM neural network is used, okay, is replicated in the general domain pre-training and in the fine-tune. And then the model is applied to traditional neural network, in this case, for performing a sentiment analysis. Okay, what we did? First of all, we trained the model from scratch. So we took 1 million sentences coming from Wikipedia, and we passed all these sentences through our disambiguator. And we transform every keyword-based sentence into a concept-based sentence. And you can see some example here. Okay, so basically where we replace the words with concepts. And then we train the ULM-fit in the same way it's been trained on the original paper, okay, from scratch. And in this case, we used a Titan RTX GPU. It took more or less 10 hours to be trained, and we use 16-bit. So you will see here a little discrepancy between the results of this training and the training on the other side. There's just very few. Here the results is 93.1% of accuracy, and on the other side is 93.5 because we used 32 bits. But you can see here that we basically used the 16-bit approximation. Okay, I don't want to go through everything, but just show you the final results at the end. So we just followed the paper and the Python implementation that is available online. And here you can see the structure of the neural network that is exactly 3 layers with the embeddings as input and some dropout at the end. And here it is. So you can see that after all the cycle of training, we reached 0.93 of accuracy. Let's switch again here. Okay, so once we prepare the model, so let's see how this model works and how this model performs. Okay, we train the models on IMDb, so we are expecting the model to work pretty well when we are talking about movies reviews. So let's load the model. It takes some time because, of course, it's running this little device. And Okay, no, not yet, sorry. Okay, now it's ready. So we have this sentence, the movie was horrible, same for the actors. And so this is the way the sentence is transformed. So the movie was, again, is the verb to be, horrible, same for the actor. And we can see, for example, that in this case, the movie is a film also called a movie. So we have the definition of movie. And we have, for example, here, horrible, provoking horror. So for every concept, we have a specific meaning. And here we are. Let's see the prediction for this text. Okay, you can see here is practically 0.9 is negative and 0.0009, so 60 is positive. So the comment is negative. Of course, we provided with a simple way to check the positivity or negativity of the comments. And here we can see that the first comment is, I found that the person, I found that person sassy and mean is negative, and awesome people for 2 hours of fun, 99% positive. And the interesting thing is that also with practically very short, in this case, one word sentences, the models still perform pretty well. I think that's it. If you have any question, I'm open to it. Thank you.
Thanks, Antonio. You have one question in the Q&A. I think I know the answer to this, but where can we find the code? Do you share it on GitHub?
Oh, okay, I will share the code. Unfortunately, I cannot share the NLP engine, but I will post a way to have access to our API available online, and there, well, if I remember, there's like 10 million characters for free, so you are free to test with our new API. You can find it on expert.ai.
Do we have any other questions for Antonio? And once again, raise your hand using the Zoom raise hand feature if you'd like to be voice enabled. Any takers? No? All right, well, seeing none, I will thank you for the presentation, Antonio. It was great to have you speaking today.